In the last video, we did a cut here and a cut here. That freed up this terminal, and this was the normal high voltage input from the solar panel, and that allows us to jumper over with a resistor, depending upon what voltage you're operating at, and operate this chip at between 12 and 15 volts, something that won't destroy the gate of a FET. I have a 13 volt center here. I just happen to have those in stock. Now, what we're doing is at the very end, and this will confuse a lot of people because you're counting pins, and it looks like this resistor, you can see these two holes here, they're in line with the IC, and many people will think this is pin 1, but it's not. That's not pin 1, that's just for the resistor. The IC actually starts at this pin. This is pin 1, and this one's pin 2. Now, this resistor is the one that we pulled from underneath. And that is this resistor right here. It goes over to the 5 volt reference. So you're putting 5 volts here and 0 volts here, and that turns on the oscillator continuously. Now what we've done is remove this, and now that resistor goes here. So now pin 1 is high, and this one is pulled to ground by this resistor. So in this configuration, it's off. Now if you notice, this is a 2K here, this is also a 2K, you have a 5 volt reference, so that means you got 2.5 volts here. So on this pin here, and that's what we did with this spare one, we now have a terminal that we can connect the pot to, and we put this little capacitor across it. I had a 0.1, so I put it there. Everything in yellow here is what's new. So this is the resistor that we pulled out, keep it the same, and we just mount it on top, and that goes over here to this little pad, and that little pad goes to pin 1. Now pin 2 used to go to this pad over here, and that's where the resistor connects to. We now connect a wire from here over to this free pin we got, and of course we put the capacitor across it to get rid of noise. So we're looking for this voltage to go above 2.5 volts, and then it turns on the oscillator. So right now I have a power supply hooked up to this thing, and I got 30 volts going into it, and the voltage divider was designed to fit around that. This is a 50K, but it could be any value. It's just the voltage from the high voltage through this resistor has to result in 2.5 volts here. There are online voltage calculators where you can tell them the lower resistor, what voltage you want, and the input voltage, and it'll tell you what the total resistance is right here. So we can, if you look at the scope, we can turn it on and off by adjusting this resistor. Or we can go over to the power supply and drop the voltage slightly, and it'll turn off. Now just this right here, you could do two things with it. You could hook, say if you have a 48 volt system, you could hook this up to your 48 volt system, and when your battery voltage gets above a certain voltage, this will turn on, and you can dump power into a water heater. You could also, on the output pins over here, you could connect a solid state relay. And if your heater is driven by AC and you have a solid state relay, these output pins would turn that on and off. Now, we're going to be adding a capacitor bank to this because it'll be connected right to a solar panel, and when you turn off, you need to store that energy someplace. And you don't have a battery. This is a battery-less system. At least that's what I usually design these to be. So you have to put the energy into the battery. And then when the capacitor charges up, this circuit will turn on, start dumping power into the heating element. Now that dumps the current that's coming out of the solar panel, but you're also adding to it the current from the capacitor bank. And so you can have a panel which is producing 5 amps and a heating element which is designed to operate at that voltage, and it needs 10 amps. So it'll draw 5 amps from the solar panel and 5 amps from the capacitor bank, giving you 10 amps. But that'll be for a short period of time until the voltage drops. And then the capacitor has to recharge again, and it can only do that when the FETs turn off. So it's a nice little system. And as you can see, you've made a couple cuts. You've pulled out this resistor. That resistor is on the downside now. You've made these cuts so you can use this terminal for an input from the control resistor. And these two resistors here symbolize the output. Now that output is 50% on one and 50% on the other. I normally wouldn't like to do things that way, just have a single output and put 2 FETs in parallel. If you put 2 FETs in parallel, they produce 1/4 of the heat. So in this case, one FET is working half the time, so each produces half the heat, but you still have that same total heat that's being produced. That's why I like to do an output that uses 2 FETs in parallel.